Hello, we are going to apply our definition of pressure to learn about pressure in a gas. So here is a simple tank in which we can put the gas, and we'll have a outside will be totally vacuumed out. So we'll have a system like this, just a construct so that we know what the gas pressure will look like. So here it says completely vacuum. So this is totally isolated, is vacuum. And then we have a tank. So this is a tank, and it's got some opening. And in the tank, there is a gas here. Just somehow I put the gas in here, and there's this lid. You might say there's a lid. So here's a lid, and so this area of cross section of the lid is A. Okay, so so there's a gas here. So there's a gas particles here, and they're moving around, and they go out and hit that, right? And this part is vacuum, right? So what's going to happen is particles will go and maybe let's look at one particle. It goes up and then comes down. So its momentum changes, which means it's going to apply a force on it. A whole bunch of particles apply force on this. So if I look at the lid, so so this is the lid, and I draw free body diagrams. There will be a force from the, so there will be force from the particles of the gas, force by gas, and then there will be weight of the lid, right? So say the lid has mass m. Then you'll have a force down, mg. And if this whole thing is not accelerating, and the lid is not accelerating, so the lid is, maybe acceleration, the lid is 0. So if I give you that problem, you will, and ask you what is the relationship between the forces, you immediately can write that, right, from the static equilibrium of the lid. And so you'll have a F by gas minus mg equal to 0. But what is this F by gas, and how do I all these particles hitting and forcing? So the way we account for that is we say, so this is the bottom of the lid, the lid is top is over there, bottom of the lid of area A, we say there is a pressure, the gas is here, gas pressure is P. So when the lid is lid is actually pushing down on the gas because of its weight, there's a reaction force, which is this by the gas, and that causes a stress in the gas, and that stress is what we're going to call pressure P. So this is pressure of the gas is P. So the amount of the force the gas will apply is this pressure times the area upon which it's acting. So this is the area upon the pressure is acting. So the force will be just pressure times that area. So this will be pressure of the gas times the area of the cross section of the lid, area of the lid in this example, minus mg equal to 0. So pressure will be equal to weight of the lid times the area of cross section of the lid in this example. Okay, so this is because I had to vacuum out, so make sure that there's no other causes of force on the lid. We can actually apply this idea to understand what's atmospheric pressure, because atmosphere will be a gas. So let's apply that to understand atmospheric pressure. All right. Okay, we want to look at how to think about atmospheric pressure. Of course, atmosphere is a gas, so this is the pressure in that gas, right? What's going on is we have this is maybe atmospheric particles, dust, and molecules, what have you. So this is some atmosphere. So if I look at a say somebody's head, so here's somebody's head, and you can say that there is an area. Let's look at the area of cross section. So it's the area of cross section. This is the area. So area A. So I'm imagining there is an area above my head, and we can say that all of these particles that are there, they form one continuous fluid. Okay, so we say this over there is a vacuum. So these are all the air particles in there. So we can say the weight of these are acting on that. That's one way to think about it. If, of course, this is just a model. Air is not fluid, continuous fluid. Particles have some separation between them. And so what's really happening over here is particles are coming and hitting with a certain velocity, and then when they reflect off, that will give me the force on that. But we're going to simulate this. We're going to say weight of all of these air particles. So how much is this? So if this is height h, which can be like 10 kilometers, you can think about some large height, and this area is A, so the volume inside will be A times h. Let's see, density of this is, we're going to use a symbol rho for the density. What happens in reality is the density actually decreases as you go up. But I'm just going to not be so particular about it. I'm going to say density is same. Our average density is rho. Let's call it just average, just remind ourselves that it may not be the same everywhere, but just some average. So that I can multiply this, so the mass will simply be rho average times A times h. And we say on this, weight of all of this acting on that area. So what's acting on that area, so if I look at this area A, what's pushing on it? What's pushing on it is the weight of air above it. So if I look at below, the gas here has to, so if whatever is here, right, whatever is here, on that there's a force of this force, so there has to be another force from, in order for these to be balanced, right? So this will be the pressure here times, so this atmospheric pressure at this point times the area, and these two, you can see they will balance forces on this material that's in that area of cross section. So so balancing this gives me P atmosphere times area. This is a force up, and the force down on that is weight of that. So this is mass, rho average, A, H, and G. And that's equal to 0. So atmospheric pressure, I can actually see where the original atmospheric pressure is actually all the weights. And the area kind of cancels out from these two. And so rho average, GH. And H is, the height the atmosphere is. So this is, we say, is the average, you can say air. So atmospheric pressure is all the weights, that the acting per unit area, right? So this is the weight, and you divide by the area, gives me atmospheric pressure. So how big is this value? Well, in terms of atmospheric pressure, is approximately 1.013 times 10 to the power 5 Pascal. So you can see the Pascal is a really tiny unit, right? Atmospheric pressure, you hardly feel it, but it's a huge number in these units. So this may not be a very good unit for all kinds of purposes, right? So you can say, well, what's a good unit? You can just call this 1 ATM. Just call that. So there's another unit for atmospheric pressure. We will learn in an experiment called Torricelli experiment that this kind of pressure, this kind of force, actually, if you use this much force, you can support 76 millimeter of mercury. So if you vacuum out the mercury, so if you vacuum out a tube filled with mercury, okay, so there's nothing up there, no air up there, and so if you let go, just like this, let go, this tube will empty out. So atmospheric pressure is pushing up, and this is 76 millimeter of mercury. So it won't completely empty out, and there's a vacuum air. So if you take a tube of mercury long enough, right, more than 76 millimeter. So this is 76 centimeter. So suppose a 1 meter tube you took, not millimeter, centimeter, 1 meter tube you took, and filled that with mercury, and held the bottom of this, and see, tube was like this, and filled all the way, and closed it, and turn it over. Mercury will empty out, but not all of the mercury will empty out. It will still hold this much, which means something is pushing it up, and that's coming from the atmospheric pressure at that point. Just outside, the atmospheric pressure is applying the necessary force that balances the weight of this guy. And so that gives another unit, 760 millimeter Hg. That's for you chemists, Hg for mercury. All right. So this is another unit that's in common use. It's like in atmospheric physics, this is one of the units that's very common use. Actually, meteorology is another unit. So this much here, we can call it a bar. So 10 to the power 5 Pascal, just call it a bar. And when the wind blows and wind pressure, etc., that's usually written in millibars. So millibar, 1 millibar will be 10, multiply everything by 10 minus 3, right? So that's going to be 10 to the power 2 Pascal. So like 100 Pascal has an actual unit, which turns out to be a very useful unit for meteorology. I'm going to stop here for atmospheric pressure, okay? And we will talk next video.